Hello. So before we get started with chapter 6 on divisibility, I wanted to talk a little bit more about historical context of how the cardinality and infinite cardinality uh, developed. And two main mathematicians that kind of contributed to it that I think is good to know. So let's jump right to it. Okay, so the person credited for really understanding infinity the first is Georg Cantor. I know his name looks like George. It's not a typo. It's Georg Cantor. He's a German mathematician. Um, he contributed to invention of set theory. And he established the importance of much of what you learned in chapter 4 about one-to-one correspondence and well-ordered sets. And first person to truly understand infinities. In this class, we talked about cardinal infinity, the size of the infinity. He also discussed a different notion of infinity called ordinal numbers and infinities. That is beyond the scope for the course, but he did a lot with that. Just quickly, ordinal numbers are kind of like not so much the size of it, but like a list of orders. So in cardinals, you only care about how many elements are in there. In ordinal, what comes after which one matters. So as finite numbers, there's no difference between cardinal and ordinal numbers in some sense. But when you get to infinities, the way you think about it as a size or order does change the meaning of the infinity. So as an ordinal number, you could do things like infinity plus 1 and still make sense of that. Although like in a cardinal sense, infinity plus 1 is the same size as the infinity. Although he developed these beautiful ideas, unfortunately, because he was so counterintuitive, he wasn't accepted right away. And he wasn't really given the credit that he really deserves. He had depression and he spent much of his later life in a sanatorium. So that's Georg Cantor. So the person that's more credited for making this idea more popular is David Hilbert. In fact, that's not the only thing he's known for. He's probably the most influential mathematician of 20th century. He is most famous for setting forth 23 problems to mathematicians in an international congress at the year 1900. So he said, hey, mathematicians, we should work on these 23 important problems. And mathematicians did try to work on them. So a lot of them are solved, but some are still unsolved as well. So he coordinated the efforts of what mathematicians should work on for that 100 years in the 20th century, from 1900 to 2000 or so. Okay. So since you learned about infinite cardinals, you should be familiar with what's called Hilbert's hotel. So here's how Hilbert tried to explain the ideas. So Hilbert has a hotel with infinitely many rooms, doors numbered 1, 2, 3, 4, and so on, all the natural numbers. And each of the hotel room is taken. It's all booked. But somebody comes in and said, hey, can I get a room? And then Hilbert says, yes, it's full, but we can move some people around. So he knocks on the door of room number 1, and ask him to move to room number 2. And then for the person in the room number 2 to move to room number 3, and so on. So person in room n goes to n plus 1. Then there's one extra room at 1 that the person could now sleep in. So the hotel is still full, but they were able to accommodate one more person into the hotel. If there was a bus, infinitely long bus, full of infinitely many people who wants to stay at a Hilbert's hotel, you could still accommodate them. What you could do is you could ask the person in room n to move to room 2n. So all the even numbers will be taken up, and all the odd numbers will be now open. So there's infinitely many new rooms that people from the bus could now take. So you could fill up so Hilbert's Infinite Hotel could accommodate infinitely many new guests as well. And you could, there's infinitely many different variations of these things that you could kind of think about that really made the idea of these one-to-one correspondence and infinity make sense to a lot of people. Anyways, when I told you about Hilbert's 23 problems from 1900, you might wonder, was there something similar at the beginning of this century at year 2000? And there is. It's not quite as many problems, but they're called 7 Millennium Problems offered by Clay Institute. And they put the prize of $1 million to each of the 7 problems, which they thought is a very important problem that mathematicians should focus on for the next 100 years. So I can't describe all of them in this video, but let me just kind of read off what they are. And I encourage you to kind of Google and look up a couple of these 7 that you might find interesting. So the first problem is Poincare Conjecture. This one is actually already solved. So it was solved by Grigory Perelman. He's a Russian mathematician in 2006. He famously did not refuse to accept the $1 million prize, but he did solve it, and he just didn't want the attention that came with the prize. There are a lot of computer science students in this class. Maybe you have heard of P versus NP problem. There's a $1 million prize on that as well. So this is a very important problem in computer science, which deals with complexities of different types of problems. So there are problems, P problems and NP problems. And the computer scientists generally agree that NP problems are harder to solve opposed to some P problems, but they can't prove that they're harder. So that's a very important problem that a lot of mathematicians and computer scientists are working on. Hodge conjecture is a little bit harder to describe, but he deals with certain algebraic shapes. Riemann hypothesis is probably the most famous out of all 7 of these problems. It has to do with distribution of prime numbers. For people who are interested in mathematical physics, the next 2 problems might be more interesting. So if you care about like quantum mechanics and all mathematical physics, Yang-Mills and mass gap is something that we really want to understand the mathematical foundation of. And Navier-Stokes equations describe, it's an equation that's not too difficult to write down in fluid dynamics that has something to do with turbulence of fluid. You could approximate solutions with computers and have beautiful results that look real, but the mathematical foundation part, like, is very difficult, and people can't write down any simple solutions to these equations. They could just approximate them. If you can even show that if there's a smooth solution to the set of equations that you could write down, then you can claim your $1 million. The last one, Birch and Swinnerton-Dwyer conjecture, I don't think I'm going to go into much either. It has something to do with algebraic object called elliptic curves that's used in some encryption and random number generation and so on. Okay, anyways, I think I want to end this video here, and then we'll get started with chapter 6 on divisibility.